In theory, it's working. All right, so today we have 4 groups in this session. We're going to be starting off with the STEM Center demo, followed by the design build fly competition, followed by Team Turbojet, and then we have the Delta Hawk combustion engine block for our 4th presentation today. Hopefully you guys know standard kind of procedures here. We're going to have 22 minutes for presenting. Try and keep to that as close as possible, and then we'll have roughly about 8 minutes for Q&A, and then it'll be rotating to the next group. Since no time was allocated for that, we're going to be racing against like F1 pit crews, so they have to do like tires, gas, everything like that. You guys just have to plug in HDMI. So are you faster than an F1 pit crew? Right? No? Okay, so in terms of setup, we'll let each group present. We'll hold any questions until the end. And then once they finish and reach the Q&A portion, this will be open for everyone. We'll try and keep to the timing as much as possible. So with that, I think we have about 30 seconds. Once you guys feel like you are ready to go. Start soccer. All right, floor is yours.
Hello, everyone. We are the STEM Center Fluid Power Educational Demo. I'm Zach.
I'm Alex.
Ian. So for those of you who don't know what the MSOE STEM Center is, they are a facility that works through MSOE to help K-12 classrooms in the Milwaukee school area get access to STEM and start kind of growing into those STEM ideologies while they're still in younger classrooms. They work through, like I said, all these Milwaukee public schools. They have schools come in, they do these 90-minute demos, these build kits that all basically teach these kids fundamental STEM ideologies. The center is looking to add a new program this year, and that was our project, specifically in fluid power. They wanted kind of a hands-on, standalone activity that can be run through the center, and the audience is upper elementary and middle school classrooms.
I'm going to take you guys through our problem statement. We have the MSOE STEM Center needs an affordable and educational demonstration of fluid power, covering some key principles such as Pascal's law, pneumatics, hydraulics, and fluid dynamics. The demonstration should be fun and informational as it is aimed at middle school students and upper elementary school students. The demonstration, along with a short informational session, should be completed within 90 minutes.
So for our constraints, while we don't have a lot, what we do have is pretty important. First off, our working fluid has to be either air or water. The STEM Center doesn't want us using like oil or anything like that. Second off, we have 90 minutes to introduce, build, and test our demonstration. 90 minutes standard a lot of time the STEM Center gives to any block of kids. Third thing, we need to be able to make about 30 to 31 kits for all of the kids that are coming over, and then an extra kit as like a demonstration kit for the teacher. So we need to make about 32 while remaining within budget. Next up, all materials and construction methods have to be, for the activity, have to be non-toxic, classroom safe, and not require any specialized PPE. That's for obvious reasons. And the final thing, all the materials for the demonstration have to be reusable. The STEM Center doesn't want to have to go buy new materials every time they put this demonstration.
So now that we kind of had our problem and what we were working with, our first step was to start our background research. And the perfect way for us to get into that was to actually go to the STEM Center. And Sarah, our sponsor for this project, she's actually in charge of the STEM Center and doing those kits and organizing everything. So buying the kits, sometimes making new kits. So we went straight to the source and kind of walked through the kits that they currently use. Now, granted, these aren't for fluid power all the time. They did have a few that were related, but these are for other principles. So we went there and we kind of took the key takeaways from what makes a kid successful at the STEM Center. One of those big things is making sure every kid feels engaged. So you have full classrooms coming in, about 30 kids, groups of 2 to 3 students per kid. You don't want one kid sitting there and he's not even doing anything, and then the other 2 kids are having all the fun and they're actually learning the lessons that come from these kids. So we want to make a kit that everyone in the group feels engaged with. Second, the theming for these kids is really important. One way to do that is to, excuse me, is to frame it like they were in industry. Someone comes to them and say, hey, Putt Putt Golf is looking for you to design an automatic golfer. Something that gives them a little narrative, a little interest in the project, so they're not just getting thrown in and they don't really care. This gives them interest. They can see a real world application of this. We want the kids to be buildable within 50 minutes. Sure, they have a 90-minute time slot. Some of that is the introduction, that 15-minute, hey, here's the fundamentals of what we're teaching you. Because these are educational kits. These are more than just like toys. These are meant to teach actual principles. Give them that narrative, get them interested, and then start letting them build. That 50 minutes gives time for the teacher to come over and help them if they're struggling, or them to actually play with the kit after it's been fully assembled. Now, some of the materials that they currently use, a lot of Lego. Again, this gives the kids a lot of creativity opportunity. They can kind of take the core principles and then add on and run with them in their own unique way. And then wood and glue kits. Again, simple for the kids to build, but they're still able to change things up per kit.
For my background research, I looked into two main things: existing products and scientific information. For the existing products, the vast majority of stuff that existed were all like fluid power, experimental educational toys for kids. So while they varied a lot in form, they didn't really vary that much in function. Everything was some sort of hydraulic piston actuation sort of thing, or some stream of water is pushing something. So for instance, what I found here is a water wheel. You would let a stream of water flow through the water wheel. I turn the gears, which can turn this red knob over here. The other stuff I looked into for scientific information, I wanted to look a lot into how effective is experiential learning. And in general, what I found was that kids that go through experiential learning, they retain the information a lot more, they understand what they went through a lot more, and in general, they just enjoy the experience significantly more than if they were in a standard lecture.
For my background research, I kind of took it in a different direction. I took those principles that we learned when we visited the STEM Center on what makes a kid successful, and kind of took that into the actual market. I went on Amazon, I went on Toys R Us, well, what is Toys R Us now, and went through what do these kits look like in mass production, that these are getting sold, and do the principles that we see from the STEM Center design kits, do they kind of transfer over into kits that people are actually buying? A lot of the themes that I saw were kind of these take it your own way kits, which goes back to exactly what we learned from the STEM Center, which is that kids don't necessarily want to build a model that's only buildable one way. To actually get the kids to fully grasp it, you have to kind of let them take it, create creativity, like take it in their own direction, and then maybe they have to fail, but that's fine. Failure is part of learning. And then part of the execution of these mass-produced kits. How are we going to actually make 30 kits for the STEM Center, make them reliably, make them consistent, and then make them reusable? So I went through and learned what's the common themes across tons of kits on the market. A lot of reusable things: syringes, plastic tubes, MDF board, popsicle sticks, things that can be used in multiple applications, yet still cheap to produce.
Moving on with some more background research, I have design inspiration and feasibility. So I went ahead and researched some open source platforms that they're made for teaching fluid dynamics, and the platforms actually put out instructions online that anybody can use to make these kits using some low cost materials that can be found in like everyday household items. These showed that these models were successful, and a lot of times they showed more success to combine these household items with like Lego motors to actuate some of that motion. And it does validate our approach, which we have are moving forward with, to combine custom wooden kits and using them with standard Lego bricks to keep the project under $1,000 budget. And then for lesson structure and engagement, I went ahead and researched some effective learning techniques for especially like middle school children, K through 12, and this showed that actually connecting these new complex concepts with students' pre-existing knowledge can help a lot. So like a lot of us here, we'll have in classrooms, we'll be learning about some new like abstract concept, and it helps me at least that I'm hopefully it helps some of you guys as well to connect these things to some more familiar concepts that we already know. So whether that's like something that we've already learned in a previous class or just something that we can really connect to like an everyday kind of thing. It can really make these really abstract concepts into something more tangible and that we can conceptualize a lot easier. So we're going to use this as well in our introduction, and we're going to start off the kids with like something a little bit more familiar. For example, for like fluid hydraulics and stuff like this, but we could start with something like, have you ever used a squirt gun, rather than all these abstract definitions and calculations. So we also found evidence that suggests that allowing students to make mistakes, as I'm saying, goes on to like help them learn and actually retain the information better, rather than having designs that are super simple or super rigid, where there's not much room for failure, or they have like very concrete instructions. We're going to allow them to actually like show some creativity and allow them to even like try it out their own a little bit and maybe fail and then retry it and ultimately succeed with the with the design. And this will not only like allow them to have a little more fun, a little more creativity in the process, but it will also help them retain the information that they're actually learning. And then, so now we're going to move on to design formulations. So all of us on our own generated at least 3 ideas and designs for this kit. And then we all came together and we reviewed these designs. And as a team, we also added some more brainstorming in, and we talked and we consolidated 10 designs total. And then from these 10 designs, we did some work decision matrices and really filtered them down. And we ended up choosing our top 4 candidates to move on to the detail and modeling phase.
This was one of our ideas. This is a super basic idea, one that the STEM Center has kind of seen before. This is one of the basic fundamentals of fluid power that we see in industry, right? Hydraulics in scissor lifts, that could be in also equipment like forklifts, tractors, construction equipment. Specifically, we pulled out one that was just a hydraulic lift, super easy, super straightforward. You would just have the one piston. In the school kits, we actually see these being just medical syringes. Again, we saw that in the industry kits as well. Each team would build a kit. They would just push down on the one piston, and it would raise the scissor lift. This demonstrates Pascal's law. And then how we were going to make this a little more interesting for the students and a little more educational was going to be using different sized pistons to show the relationship between the area of the piston and the force required to lift the scissor lift. And we kind of make this more like a lab. You set weights on both the scissor lift, and then you could apply a set weight to the syringe, and you could see the direct correlation.
So going on to the hydraulic shovel, again, each team will get a build kit, and inside these build kits, they'll have all the materials they need to build the shovel. They'll have vinyl tubing and syringes, which will act as pistons, and they can push down on these to actuate the movement of the shovels. And this successfully demonstrates Pascal's law as well as some other basics in mechanics. So for the hydraulic claw, these were both very similar ideas. They're conceptually very similar, just a little bit different in form. As you can see, like the actuated motion, this one is a claw instead of a shovel. So again, each team will get a build kit. Again, they'll be able to build the actual model themselves and make all the connections. The pistons will be vinyl tubing and syringes, which will actuate the motion of the claw. And they can use a little bit more pistons in this design, however. And this also demonstrates Pascal's law.
And the final thing we came up with was a simplified version of a fire truck ladder. What this is supposed to be able to teach the kids is both Pascal's law and some basics in energy conservation. So how it would work is we would give each team a single kit, and then they would go ahead and build their kit. The fire truck ladder would have 2 pistons, one to actually raise and lower the ladder, and a second one to extend the ladder outwards. Those two pistons would then be able to show them Pascal's law by showing the relationship between two areas of the pistons and then also the amount of force required to move everything up and down. The other thing we'd be looking into, or the other thing we'd have on there would be a fire hose that's being run by a pump. That would be able to simulate like actually running a fire hose to be able to go put out fire. For the pump system required for that, we'd have to build it and just give it to them because that's something that's kind of out of their scope. A bit too complicated for like 13-year-olds. But that fire pump system would then be able to show some basics in energy conservation, so they'd be able to see like as we lower the ladder, the water goes faster. So once we had all of our ideas down, we decided we need to be able to figure out like what we actually want to keep and what we don't think is very good. So we decided we would use a decision matrix. We graded everything we had off of 5 different criteria: student involvement, educational value, feasibility, engineering complexity, and finally student difficulty. Student involvement is basically just, we wanted to make sure every student there was doing something, working together, and no one was just sitting in the corner twiddling their thumbs. Second thing we were looking into was educational value. We wanted to make sure that the students that came to the STEM Center actually learned something and weren't just like playing around with toys for 90 minutes. Third thing we wanted to grade off of was feasibility. Feasibility was all about how realistic do we think this is to actually be able to, 1, build it, 2, have it in a classroom, and 3, how likely do we think we are that the STEM Center is going to be okay that we're actually going to do this. The final thing, or no, second to last thing was engineering complexity. That's something more just for us. We didn't want to come up with something that was like super simplistic and then kind of lame to present. Just because this is still an engineering project, we want to make sure we come up with something we're actually proud of. Well, it's ultimately, that's also just for us. The STEM Center doesn't get anything if we make something super duper complicated. They don't get anything out of that. So that's why it's rated the lowest out of everything. And finally, student difficulty. If something is really, really complicated, students aren't going to get anything out of it. They won't be able to understand it. But if it's also really, really easy, they're not going to be challenged. They're not going to get anything. So we were looking for that like Goldilocks zone of right in the middle. Once we had finally graded everything, we had found that the top stuff were the shovel and the hydraulic claw at 3.65. Second thing was the fire truck at 3.55. And in fourth was the hydraulic lift at 3.15.
Now that we had our 4 finalists, we went back to the STEM Center and talked to Sarah again and walked her through every single one of those, what they would entail, maybe what they would look like to the students, the lessons we were trying to teach. Sarah really liked the fire truck ladder. Although it wasn't rated highest on our decision matrix, it was everyone's favorite as well. And it got selected for its strong narrative, high engagement, and educational depth. We were a little worried about the water in the classroom with middle schoolers. Sarah did say that was okay. Maybe some bins underneath the kits to collect the water, make sure the kids aren't making too much of a mess. And then we updated our project scope to manufacture 30 complete kits that were robust enough to be disassembled and reused for multiple sessions. This is just a generic model that we made, just to kind of show a proof of concept. Again, we do want these to be custom built by the kids. So these are not going to be totally pre-made kits. There is going to be some creative aspect of this. Maybe these could be Lego built with some 3D printed parts that would interact with Lego. Specifically, we're thinking about these syringes. These would need to be able to interact with Lego in order to still give the kids something that they can build on their own, while also allowing them to be creative, but still use pre-built parts. So this is just a proof of concept. Just a little exploded view again. These would be custom made syringes that would either interact with Lego or 3D printed parts or wooden parts, something that the kids can build on their own. And then just a little motion just to show how those syringes interact, maybe. Go one more. Oh, there we go. Slide again.
Now that we had our final design, decided upon, what we needed to do, what I decided I wanted to do next was do some preliminary calculations based around like the geometry of the model. For all of these preliminary calculations, because we don't actually have any like hard numbers yet, everything was kept in variable format. So the first thing I wanted to look into was the speed of the water as it exits the hose. So what I started out with is I started out with Bernoulli's equation, and then I made two key assumptions. First off, the pressure of the water at point 1 and pressure at point 2, those are both going to be equal. They'll both be atmospheric pressure, so we'll cancel each other out. And the second thing is we're going to use a large reservoir assumption. So V1 will be basically 0, and that can also be ignored. I took those assumptions, plugged them back into Bernoulli's equation, solved that to find V2, and this is what I got. Second thing I looked into was the actual lifting force required to be able to lift and raise the ladder. So I started out here with Pascal's law. The pressure in the two pistons has to be equal to each other. Then that can be expanded into the actual forces and areas in Pascal's law. So ultimately we end up with force 1, which is the force required pushing down on that piston. That is equal to the ratio of the cross-sectional areas of the two pistons multiplied by F2, which is the force acting on piston 2. Out of that whole thing, the only thing we don't know is F2. To be able to go find F2, I looked at all of the forces acting on the ladder itself. I decided the easiest way to determine this, take a sum of moments about the origin, and the only thing I didn't end up knowing was Fw. Fw is the recoil force of the water as the hose is spraying the water. So if you've ever like cranked a hose and then let it go, the hose starts to go all wild. That is that recoil force acting on the hose that's blowing it backwards. To be able to determine that, I had to go look it up what the actual equation is. It is equal to 2 times the cross-sectional area of the hose multiplied by the difference in pressure between the inside of the hose and the outside, so like the atmosphere. To be able to determine what that was, again, going back to Bernoulli's equation, and then I just solved to be able to find the difference between P2 and P1. What I found is and then I plugged that equation back into Fw. Then I took this equation for Fw, plugged it back in here to solve this for F2, plugged it back in here, and then finally this is the equation for F1. The final thing I looked into was the required force to extend the ladder. Again, starting out in a similar place, Pascal's law. F1 is equal to the ratio of the cross-sectional areas multiplied by F2. Again, we don't know F2. To find F2, looking at all of the forces acting on just the extension part of the ladder, not the whole thing this time. So to be able to determine that, looking at the sum of the forces in the Y, sum of the forces in the X. For the sum of forces in the X, we need to be able to know what the force of friction is. To find the force of friction, we needed the normal force. So we went back to the sum of forces in the Y, solved for Fn, took that value, multiplied it by the coefficient of friction, and plugged that back into Fx. I solved that equation for F2, and then you'll see that it also has, again, the recoil force of the water. Took the same equation from before, plugged it back in here, plugged all of that back into this equation all the way up top to find finally what F1 is, and it's this really long.
So moving on, we're going to talk about nitrogen spray. So we have some manufacturing plants. We discussed we want to make around 32 kits now, and we want to utilize some laser cutting or CNC routing for wood structural components, and this will ensure precision and uniformity across all kits. We're going to standardize mold facing so we can seamlessly interface them with Lego parts and use them with mixed pins and bricks. Then we're also planning to pre-assemble the hydraulic pump and hose systems as we discussed. And this is because this can be pretty difficult for students, K through 12 to be doing with hands-on. And this will also make sure that they're leak-proof and they're also ready for the classroom. In order to stay under our $1,000 budget for all kits, we are going to do some bulk purchasing of tubing, syringes, and Lego components. And that also brings us back to cutting out our own wood structural components. And now to go through documentation and curriculum. So we plan to create some visual nonverbal instructions to guide students through the build process. We're also going to develop the around 15-minute educational script explaining Pascal's law and how it applies to the fire house extension and lift. And we'll also go through some of that energy equations. And finally, we're going to conduct a dry run with the STEM Center staff and verify the timing and the durability of the kits.
Thank you, guys. We'd love to open the floor to questions now.
So one question I had was, I really like the sort of the ladder idea, right? That's super neat. But I guess in my mind, with your initial brief of wanting it to be foster creativity where they could do different things with it, I don't think that's immediately apparent with your final design, in the sense that it's always going to boil down to that sort of extending ladder to pumps, and it's going to do the same thing. So I was curious, like, when you talk a little bit about the creativity aspect of it, what are some of the things that they could do from, say, session to session that would be different than what you presented?
So,
Does my question make sense?
yeah,
Yeah.
So, one of our big things we were looking into is we wanted to be able to have, an amount of creativity, because we wanted to give the kids some autonomy, so that when you actually have some control over what you're doing, you tend to learn better. So what we wanted to do was we wanted them to have like some control over what they're doing. So having them be able to put different parts together would kind of push into that idea of creativity. And then like some things we didn't mention here, but like we would talk about, we probably were gonna do is we would have like different size syringes, so they can still have like those different stuff and still see like, oh, I wanna be pushing the idea of creativity. Oh, if I switch these two pistons, pushing this is a lot harder than the other, so stuff like that.
Perfect. Okay.
Anyone else?
Could you go back to slide 14? So when you were evaluating all of these, and I think, so the ones you have highlighted in blue were the ones you went through.
Yeah.
Those are the ones that I've done.
Those are always, okay. When he gets to the student difficulty, and I think you mentioned this as well, you want something that's difficult, but not too difficult.
Yeah.
Right? So how did you rate one?
So it was kind of difficult because ultimately what we were looking for is not. We don't want really high, we don't really want really low, we want right in the middle.
Yeah.
So if you imagine like a normal distribution, that highest point is your 4, and as you get farther and farther away, you get 3, 2, and 1.
Yeah.
So we put ourselves in the shoes of like these students and thought like, okay, in the amount of time that we have, they're middle schoolers, they're smarter, but they're not like super duper smart. So we thought, okay, what is something they can, well, not middle schoolers, but like if you were in middle school, you get that.
And you're on video.
But okay, the point is, like they don't need, we wanted something that we figured they could realistically do without like pushing themselves to the edge, but like still something that they're gonna be able to have to engage with it if they want to get anything on.
So a 4 would be at that optimal level.
Yeah, a 4 would be.
But 2 could be on either side.
Yes, 2 could be either
Okay.
too hard or just
Yeah.
slightly too easy.
Okay. And then the last thing, boredom avoidance is really big.
Yeah.
And you're kind of around it with student involvement, things like that, but, something that it, encapsulates fun or engagement or something like that, I would suggest putting that, as an evaluation criteria.
Okay, thank you.
I have 2 questions about your analysis.
Uh,
So that's, when you talk about some of the verbally stuff. Yeah, okay, so the first line here. One thing is, you said there's a nozzle at the end, right?
yes, over here.
So that would, this is gonna be a minor effect, but that would tell me that the velocity is not gonna be constant throughout the pipe system, right? Because I would imagine B2 is gonna be different than what the velocity through the actual rest of the pipe is, because there's an area contraction at the end, right?
Well, I say
Or-
nozzle, it's a cut end of the tube.
Okay, so it's a constant diameter throughout.
Yes.
Because we're gonna be using that plastic tubing, we're not actually gonna manufacture a nozzle.
Okay,
that actually
okay,
narrows
all
down.
right, so that's what I wanted to clarify. Okay, cool, and then can you move forward to the next one? So when you're talking about the recoil force, to me, a relatively straightforward way, because I'm not 100% clear where you're getting 2 times area of the hose, P inner minus P outer is from. But a relatively straightforward way I think you could do it is just do a linear momentum analysis of the flow going through the pipe. And that acceleration and change in direction is going to be equal and opposite to the force that it's going to apply on the ladder, right? So I think to me, that would be a more concrete way to get something compared to that, which to me, unless you can expand on it, I'm not fully.
So it's funny you say that because when I was trying to do this math, I was thinking for a really long time, how am I even supposed to figure that out? I had thought of that idea, and so I was playing around with like force and momentum and stuff like that, but I couldn't. Granted, this was back then after, so
Yeah.
grain of salt, but I couldn't figure out what certain values were going to be.
Sure.
So I then decided, okay, I should just look up like what's the recoil force of like a squirt, not a squirt gun, but like a hose or something like that, and just use that. And this is what my research.
Okay. You might find if you do the analysis, it might boil down to the same thing, but at least you're like, okay, I know exactly where this is coming from. And then on the same slide, my last question, I promise. When you talk about the lifting force, I'm guessing this is just a static force required to hold this thing up at a given angle. Is that correct?
Yeah.
Okay, so you're not looking at what's the force required to actually move it at a,
No, we're not,
how long?
we're not looking at the force to technically overcome
Okay.
anything like that, because then also you have to care about like, there's rotational friction here and stuff like that.
Yep.
We were just looking at like, what is the static force to just hold it.
Thank you.
All right, so I think we are getting close on time. If our clients want to ask any really tough questions, put them on the spot. All right, otherwise we'll go ahead and thank our first group. And then we'll move to our second group, which will be the design, build, fly presentation. So, and thank you guys for coming.
Yes.
Thank you. Really nice to meet everybody.
By the way, Liz.
Yeah.
I think the renewable energy club, we're still looking at those wind turbine kits. I don't know, sometime maybe next year, touch base on
Yeah,
that.
definitely.
Okay.
Sarah, she was meeting with the
Okay.
president of the club.
Yeah, yeah, like they were working on it and then they kind of got paused and they got some other ideas going and I was like, I really should need them to get something
Yeah.
kind of out and seriously down the line.
Ebb and flow. So yeah.
Yeah.
we're looking-
All right, sounds good. Well, have a good break and enjoy the holidays. All right. Okay, so almost as fast as F1, but cutting it close. So with that, we have our second group. This will be the Design Will Fly team. They'll go ahead and introduce themselves. So whenever you're ready, floor is yours.
Welcome everyone. Design Build Fly, Senior Design Progress Report. I am Erin. I have been working primarily on the landing gear and the banner.
I'm Logan, I did CAD and propulsion. I'm James, I worked on wing design. I'm Marcus, I was looking at control surfaces.
I'm Chad, I did storage and passengers.
Matt Callaway, and I did the structure and materials.
The American Institute of Aeronautics and Astronautics puts on a yearly design, build, fly competition for students to take their theoretical knowledge and apply it to real-world airplane building experience. We will follow all the rules of the competition, but we are not going to be competing this year. The 2026 mission in particular is a charter bush airplane. The mission is to conduct charter flights carrying passengers and cargo to pay for the airplane and the banner towing business. Our passengers are 2.3-inch rubber duckies. Our cargo is a standard hockey puck, and our banner will be deployed during flight and released at the end of the flight. The first mission is a test flight. There will be no payload. You must complete 3 laps in the 5-minute flight window. Successful flight includes a successful landing, and then we'll receive a score of 1. Mission 2 is the charter flight. Passengers and cargo will be carried, at least 3 passengers, at least 1 piece of cargo. You have the same 5-minute flight window to get as many laps as you can. The score will be based on passenger count and number of laps completed. Mission 3 is the banner flight. The banner will be deployed at the first upwind turn of the flight course, and banner will be released after the completion of the final lap. The score is based on banner length, laps completed, and rated airplane cost, which is a function of the wingspan length. The ground mission is a timed mission. First, the passengers and cargo will be stored. The pilot will then demonstrate flight controls. The passenger and the cargo will be unloaded, the banner will be stowed, and the pilot will again demonstrate flight controls. The score will be based on the lowest team's time and our team's individual time. We'll extrapolate the lowest team's time from other timed missions and past years.
There are a handful of different constraints relevant to the propulsion system. One is that the total stored propulsion energy must be less than 100 watt hours. Your battery must be nickel cadmium, nickel metal hydride, or lithium based. The prop must be commercially available, and the arming fuse must be mounted externally and has to be at most 100 amps. So we first looked at where we are going to put the propulsion system and how many propulsion systems we are going to have. After some consideration, we found that using a tractor design with 1 single motor is the most effective. It's easy to integrate, it's simple, and it's efficient. In terms of sizing the propulsion system, we took our total stored energy, looked at how long our flight window is, and used that to figure out what the power rating of our motor should be. We made sure to consider that with a lithium-based battery, you're only supposed to use about 80% of its capacity, and that we likely will not be operating at 100% throttle. It's typically more ideal to be operating anywhere between 50 and 75%. So we found a handful of propulsion systems that may meet our need. Thrust is an estimate based on propeller and throttle. That being said, we're looking at about 6 to 10 pounds of thrust. In terms of current, all of these motors are less than the 100 amp maximum for our fuse. These motors typically run on 4S to 6S batteries, S being the number of cells in the battery. So 6S battery has 22.2 volts. kV is a parameter for how fast the propeller is spinning, and it is based on how many volts you apply to the motor. Some additional considerations we had. In terms of sizing the propeller, there's a couple main factors. There's the diameter of the propeller, the pitch of the propeller, and then the hub diameter to match your motor. Broadly speaking, a larger propeller gives you better thrust and is more efficient, and a lower pitch prop is slower, but kind of pulls through the air a little harder. In terms of the battery, we need to make sure that we are within our propulsion energy limit, so we can calculate the capacity by dividing our energy by our voltage. The ESC and the fuse must match the current ratings of the system, so whether that is the motor or the ESC, the fuse has to match. So what we know right now, we are going to use a single tractor motor. In terms of power, we're looking for anywhere between 1,000 and 1,500 watts. We're probably going to go with a 6S 4,500 milliamp hour battery with a large diameter prop and a low pitch. And then our fuse and electronic speed control will match. Looking forward, we need to select the exact brand and size motor. We need to select a handful of propellers, and then we need to test the combinations of those systems to make sure they meet our thrust and kind of flight duration needs.
All right, we're looking at the wing, we only got a couple constraints. A couple simple ones, it must be a fixed wing aircraft, it cannot be a light up in the air configuration. The main constraint here was the wingspan had to be larger than 3 feet, while remaining smaller than 5 feet. The smaller wing can receive more points than mission 3 of the banner. However, a larger wing has a higher point potential that affect the passengers and cargo mission. To help decide on a wing geometry, we consider 3 designs here. We have a straight rectangular wing and 2 tapered designs. The benefits that come with the tapered designs being maneuverability and efficiency can be negligible at the slower speed and on a small scale. So we chose the rectangular wing because it's the easiest to design. The wing position, we did not matrix. We have a low wing, a mid wing, and a high wing. The low wing and the mid wing can be really hard to implement on the small scale again, because we have a lot of passengers and cargo. You have to have spars running through that space. So we selected a high wing. The lift equation, this helps to decide the size of the wing as well. We have 5 variables in the lift equation, so it took an iterative process to narrow down each of the values. The lifting force we set to the weight of the airplane. After research, we found that typical planes this size, typical with the materials that we'll talk about, they're around 8 pounds. The lift coefficient we found based on airfoils that we cover in the next slide. The surface area we determined to be just under 5 feet. This is due to our 5-foot wingspan and aspect ratio of 5:1. Again, with research, we found that the typical aspect ratio of a bush plane is somewhere between 5:1 and 7:1. So we picked a 5:1 aspect ratio to give us like surface area. And then we solved for velocity. That gave us a speed of 44 miles per hour to keep the plane in the air at 11 feet. The lift coefficient took the most amount of work here. So we compared several different airfoils using the airfoiltools.com website. It's really helpful because we were able to plot airfoils against each other. And that way we can compare the lift coefficient among the angle of attack. So here it's an NACA weight profile 4412 next to an NACA profile 2412. The only difference really being that camera angle. So 4412, you can see that gold line has a 0.5 lift coefficient at 0 angle of attack compared to 0.25 to 2412. So that's kind of how we selected that one. This is just a 2D assumption. When looking at a 3D wing, we have to consider conversions. This was more of background research from a textbook we found. Due to flow separation of the wing tips, you don't actually get that 0.5 lift coefficient, you just never choose. So I'm looking at drag. We just did a simple analysis of this. We took the velocity from the lift equation and plugged it in, and then we had to find a drag coefficient again from that website, looking at the 4412 wing profile. This is just induced drag. We got a 1.29 pounds induced drag. There's also parasitic drag going on. At this time, we consider it to be negligible. The next semester we'll have to do further studies on that. So our current wing solution, we will require a 44 mile per hour speed on plane in the air. That's at a 0 angle of attack with our wing. Our wing is currently just under that 5 foot for a little air consideration. We have wing chord of 12 inches to that 5:1 aspect ratio, and our plane is 8 pounds. Next semester, we will have to pick a wing incidence angle. So this is the offset angle of the wings compared to the fuselage. That might give us a higher lift coefficient. We have to further look at the drag calculations, find what we estimate, and then we can select order to make sure we have the most count the drag.
Yeah, so taking a look at tail deflection on the aircraft, we looked at 3 different tail solutions. We looked at conventional, T-tail, and H-tail. H-tail was especially, we were looking at that because of the compatibility factor with the banner. We were considering loading the banner and restoring it right here in between the 2 rudders. But the simplicity and the structural stability of the conventional tail is really what made us go with that one. Just being able to connect the stabilizer directly to the tail section makes it a lot more structurally sound. Next, looking at some very preliminary tail calculations, just to get an estimate of the sizing. So this equation here relates the surface area of the stabilizers to the surface area of the wings. And that gives us a horizontal stabilizer surface area of 0.776 feet squared and vertical of 0.466 feet squared. Then using this and some other small aircraft that we took a look at, we found that the elevator is about 30% of the total surface area, and the rudder is going to be about 40% of the total surface area. These are really just preliminary, trying to get an initial sizing for the tail. We're going to have to look at some more, do some more calculations second semester, looking at drag and lift, and especially some forces on the control surfaces there.
So the passenger cargo portion of the flight is going to be limited to a single passenger compartment where all passengers must be on the same horizontal level on flights. At least one cargo compartment that is completely separated from the passenger compartment with a reinforced bulkhead. Both passengers and cargo must enter the fuselage with their own respective hatchway, and both passengers and cargo cannot be speed loaded into the plane unless they get loaded in at one at a time. The current conceptual designs that we currently have for our passengers is a removable wood-based carrier module for its lightweight and durability, for a symmetrical pattern for high density passenger constraints within the fuselage. Each duct is going to be secured by a stem to ensure its proper orientation upward while they're in flight, as well as a compression restraint system to keep the passengers facing forward in the direction of the flight. For the cargo, it is a 3-printed base with a sliding plate with multiple different attachment points, lots of bands to induce a compression force. Initially, it is going to be 3D printed, but we're looking into different materials for its lightweight and durability to ensure proper flight. Placement of the passenger and cargo considerations is either going to be the cargo is going to be in front of the passengers, behind, or directly below. After careful consideration of the weight factors and the different criteria, including the central gravity, the manufacturability, and the proper operations of the bushcraft, and through the proper scoring, we decided that the placement of the cargo in front of the passengers on the same level plane is going to be the most accurate for its simplicity in respect to the geometry inside the fuselage and the ground speed loading factor.
So the main constraints with our banner were the minimum length needs to be 10 inches, the maximum aspect ratio needs to be 5. It must feature the MSOB logo, must be stowed on the outside of the airplane, it must remain vertical during flight, and it cannot sustain damage during flight or landing. Some materials that we are looking to drag test in the spring are ripstop nylon in a variety of densities, as it's tear resistant and easy to sew, and low density polyethylene as it's smooth and available in a wider variety of sizes. We are looking to drag test these materials in the coming semester in order to know how their material properties interact with our flight speeds. Our banner mounting location, we are considered under the fuselage and under or on the tail. This was chosen for stowing simplicity and stability during deployment and release. And we went with under the fuselage for that simplicity of construction. The banner mechanisms, to remain that vertical orientation during flight, we are considering a top banner edge sleeve, a top trailing corner parachute, a leading edge rod, a leading edge weight or streamers at the end of the banner. These all have different compatibilities with different fabrics and sewing abilities. So we will be testing these in the coming semester to get drag numbers from that and see which one's going to be our final option. As well, our deployment choices, we are debating between a hatch mechanism and a spring and hook mechanism to be released by a single servo. And for release, we are also planning on a single servo channel for that. And we are considering a pin release, a hook release, or possibly a quick friction release. All of these we'd like to test in the coming semester to see how they perform up at those flight considerations that we are continuing to iterate.
So we considered 5 materials and evaluated them with respect to weight, strength, cost, manufacturability, being how easy they are to work with during the construction process, and impact resistance, which is crucial for the landing of the aircraft. And balsa and basswood were selected due to being lightweight, very inexpensive, and easy to work with. So the primary working material will be balsa, with basswood supporting more like critical loading points, such as like for the motor, landing gear, and the tow motor of the banner arm. For structure, so 5 conceptual structural designs were examined with respect to weight, strength, manufacturability, cost, and storage space to complete missions. Structure 3 is based off of reinforced ribs connected through longitudinal spars throughout the aircraft. And structure 5 is a conventional 3D truss design. Structure 3 has a lot of storage space. Structure 5 is very strong, and we decided to kind of merge the two to get the best of both worlds, depending on where in the fuselage. Oh, and if you go back, the final structure will be coated in monocoat, which is a thermal shrink wrap material, and that is the standard for the radio controlled aircraft. So as you can see, we've got the two different kind of designs, and this modular design will really support the mission requirements of having to have separate like cargo, passenger, and propulsion bays. And our design balances strength, weight, cost, and manufacturability to ensure success in the missions.
So our main considerations with the landing gear were its ability to interface with the banner during its deployment and release. And also whether or not we were going to use a prefabricated or design landing gear, and whether or not the single wheel was going to be steerable. Our two kind of designs that we were discussing were the tail dragger design with the two main wheels up under the wing area and the single wheel back by the tail. And the tricycle design where the two main wheels are up under the wing as well, but the single wheel is up closer to the nose. We have gone with the tricycle design because of its compatibility with the banner deployment and release.
So for the preliminary designs, we have four that we are presenting on, but the first one, we examined how an aircraft with a smaller wingspan of 3 feet and tail dragger configuration would fulfill all the missions with a side of the airplane as the banner mounting position. And then for design 2, we examined what wingspan in the middle of the available range would look like, along with a conventional tail and a tricycle configuration. Design 3 looked at larger 5-foot wingspan, a partial fuselage spar design, and an H-tail. And then design 4 is very similar to our current working design, large wingspan, conventional tail for simplicity, and a tricycle configuration.
So our current working design, you can see our current CAD right here. We've got a single DC motor here. The cargo storage in the nose section, the passengers are in the base section right behind it. And then we're planning on storing the banner in this tail section here. The banner is going to be in kind of a U-shaped bay, because one of the rules for the competition is it still needs to technically be outside of the aircraft, but we still want to keep it out of kind of the winds and kind of tucked away. We're going to go with a tricycle landing gear, and then again the NACA 1412 profile for the wing, and the NACA 0015 profile for the stabilizers on the tail. For our proposed control scheme, we have a 6-channel receiver currently. So we have 1 channel for the motor, we got 1 for the ailerons. This can be split between 2 servos. We got 1 for the rudder, 1 for the elevator, and 2 for the banner, 1 for deployment and 1 for release. And just looking at some major dimensions here for our current design, we've got a 58-inch wingspan, which is just underneath the 5-foot limit. We've got a 66-inch in length, and then 7 inches by 6 inches for the fuselage for plenty of passenger and cargo storage.
Yeah, so looking to next semester, we are going to continue to rework and revise the CAD. We're trying to keep in mind how we're going to assemble things, how we are going to manufacture these individual pieces, mostly being with the laser cutter, and where are loads being transferred to and from. First thing when we get back for break, we plan on assembling a prototype of our wing. That way we can make sure that it meets our needs and is plenty strong. We see plenty of potential for some FEA simulations, whether on the wing, on the nose section, on the landing gear, or where the banner will be pulled from. On our control surfaces, we're going to do some calculations to identify what servo torques we need, so we can appropriately size our servos, and we need to do some propulsion testing. So thank you guys for being here. Does anyone have any questions?
Something maybe I just misunderstood. You said the cargo's gonna go in the nose. Where's the motor for the propeller going to go?
So the motor will be mounted at the very front of the nose. If we could back up,
Okay.
maybe one more here. Oh, two more. So the motor will be mounted externally. We'll have to run some wires in here. I believe we're planning on putting the battery maybe in these first two bulkheads, and then these back two here can store the hockey pucks. The nose is quite a bit bigger than the individual cargo, and I believe that we will have plenty of space to store the cargo in that front section there. Yes.
You said 8 pounds for the weight of the aircraft, is that right? Does that include the cargo and the passengers?
It would,
Okay.
yeah. Looking at similar size, either commercial ones you can buy, they usually come in at about the 6-pound range. Given we're loading it with cargo pucks, we're loading a banner, we're loading ducks, we expect that'll add maybe 2 pounds. So we think that's a pretty accurate guess at this point.
When you decided on the single engine configuration, you talked about that it seemed to be the most efficient. How did you judge the efficiency of that configuration?
Yeah, so the big thing there is that you need an extra battery and an extra speed controller. Your propulsion system can only have one battery per propulsion system. So we couldn't use one battery and split it into both motors. So between adding a speed controller and a motor for each battery, the motor would have to be smaller. Each battery would have to be smaller. We settled on the fact that that adds additional weight and therefore would be less efficient.
Thank you.
When you assess the lift, you were looking at the weight of the aircraft, right? Did you look at different points in flight where you would have to look at different lift? So you're gonna have to exceed, lift's going to have to exceed weight to get it off the ground. The lift's gonna change, I don't know what altitude, probably not that high. But there should be, when you design for that, there should be some headroom, for, turbulence or wind shift or something like that. So if you get a section wind or something like that, things like that. So just something to consider when you're looking at that. And then also, for drag, you mentioned induced drag.
Yep.
Could you, one, briefly describe that? And then two, does that include the banner?
I did not. That's right. So the induced drag, that's just the drag that the airfoil itself is producing. Right, because you're producing wet dress, producing drag. Parasitic drag comes with the wing and fuselage. Right now, I said it was negligible. It's probably a poor choice of words. The induced drag does make up the majority of the drag that it's doing, but we will have to look more at the parasitic in the future. Banner is going to add a considerable amount of drag. That's why it's important. I think our motors that we're looking at right now are between 6 to 12 pounds of thrust, and the induced drag is, I think, it's around 1.3 pounds. As long as right now we're looking at good numbers, there's more work that needs to be done next semester to find out the drag of the banner. That's something that I think I mentioned as well. That we'll be doing some really preparations on.
It's a challenging requirement. It's,
Yeah.
Deploying that and
Yeah.
pulling that are going to be fun. Do you have any, last question, do you have any plans for wind tunnel testing and in any way instrumenting the plane to compare it to FBA?
Thank you. Yeah, we're trying to see if we can get the wind tunnels fast enough for starter. So that's something that we don't control.
The idea being that we could test the banner in the outwash of the wind tunnel.
Yeah.
We did play with wind tunnel testing maybe a little bit. It sounded like quite a bit of work for what we would be able to get out of it. So we hadn't put too much stock in it.
Yeah, I mean, probably doing everything at the same time would be difficult, but maybe different components.
Right, maybe some of the release mechanisms, as far as the fabric components, really can't be scaled down. So like, if like the banner is going to be sewed or things are going to be applied to either painted or sewed on, you can't really scale down that effect on like the stiffness of the banner. So it'd really be good to get those drag numbers from the full scale test, but some of the release mechanisms and deployment mechanisms perhaps could be tested at that small scale.
Because remember, what's the size of the banner again?
That's up to, it must be at least 10 inches. It must have an aspect ratio of 5. So it could be 10 inches by 2 inches is like our smallest option.
Okay.
It could be, I mean, they did this competition similarly with a larger battery in size,
Twice the battery.
Right. In 2020. So we have a little bit of like sizing ideas from them, but some of them did like 32 foot long. banner. So like there are really crazy things I don't think we'll be looking at sizes quite that large, but we'd like to test a large range.
But super last question then is, at least for me, is, why are you not competing?
So the competition requires half of your team to be undergraduate, freshmen, sophomore, underclassmen, undergraduate students. And we don't have that, and that was sort of to figure out.
Ways to keep saving down projects.
That makes sense.
Just one question, have you talked about the connections, are you using glue,
Yeah.
screws?
Glue. Yeah, mainly with glue. We're really gluing them like interlocking in the section. Yeah, like we don't plan on just space going the nose to the rest of the plane. I wasn't interlocking. That's the instructions.
One more question is, how do you verify your result? Like FEM results or use hand counts, like aerodynamics results? How are you going to verify them?
With respect to,
Experiment, like if it is calculations are correct.
so we can do, loading tests. To validate that.
Yeah, so we have right now like that, I think it's just a foot wide. We're gonna make a full size wing and we're gonna put some weights on it next semester to start with. Just to make sure that wing is strong enough. Yeah, something like that.
So when looking at your payloads, how did you ultimately decide the number of ducks and pucks? And what is that number actually in the end too?
Well, we established, 16 ducks to 1 puck. In the equations at the beginning of the slides where it did show the score system, pucks do have a more points added, but it's also more penalty when it comes to the cost in comparison to the net income. So we decided to make sure that we have a max amount of passengers with respect to 1 cargo piece to ensure that we get the most amount of points possible, while ensuring that we are going to be as light as possible to make as many launches as we can within our allotted budget.
Is it a requirement that the ducks are like oriented as a passenger would be in the aircraft? Okay, I didn't know if you could like put ducks upside down.
That makes sense. Well, I mean, we're trying to make this as somewhat realistic as possible. I mean, flying backwards in the plane is fun, but it's not quite as safe. So we're trying to be kind of realistic as much as we possibly can, but maybe for some experimentations when everything's all said and done, we'll just cram the entire plane as full of as many ducks as we can. We'll see what happens.
Awesome, thank you.
All right, so I do think that is the time that we have. So let's go ahead and thank this group. And at this point, we'll be turning it over to Team Turbojet, who are still racing against the F1 clock here.
Merry Christmas.
We'll see. All right, so with that, we'll go ahead and turn it over to our next team. You guys have the floor.
This year's design team for the S206 team. I'm Tim, this is Lizzie, Connor, and Noah, and this is our mascot, Timothy.
The goal of our project this year is to create a fuel injection system for the existing turbojet engine that was designed by a senior design team last year. We are going to enable multi-phase and multi-fuel injections, so 1 liquid fuel and 1 gaseous phase fuel for this engine, and prepare it to be self-sustaining for future laboratory experiments. A turbojet engine is a thrust-producing engine used on a lot of different aircraft, not so much anymore. But air enters through the compressor where it is increased in pressure, sending it into the combustion chamber where we add energy in the form of fuel, which then goes through the turbine to extract some of the energy for the compressor. The rest goes through the nozzle to produce thrust. On the left-hand side, you can see a very stereotypical aircraft engine, and on the right-hand side, you can see ours, which is a little bit less traditional. Last year's team used an automotive turbocharger, which is a turbine and a compressor that are centrifugal instead of axial, to then duct into a combustion chamber and then back out through the turbine and the nozzle to create a less traditional turbojet engine that produces thrust. In addition to that, they designed an oil delivery system that would deliver oil to that turbocharger, as well as a bunch of instrumentation to measure key parameters like the compression ratio and the temperature at the exit of the combustion chamber, and they're using gaseous propane as their fuel. This year, we have many objective specifications and constraints, but we're going to direct you towards a couple of key ones. Like I said, we're going to enable multi-fuel, multi-phase fuel injection, as well as achieve sustaining gas turbine engines. So last year's team did not enable self-sustained, which is one of the enables for us this year. In terms of specifications down the middle, again, we have a lot of them, but the most important to us is enabling a stable, consistent, and simple startup. If you're going to use this for future laboratory exercises, we want to ensure that the startup time is short and that it's very straightforward for any professors or students that are going to do it. Finally, with the constraints, again, we have a lot, but the most important ones to us are ensuring that our budget stays under $2,000 and that our fuel injection system can integrate with the combustion chamber that was designed by last year's team, because they did a lot of good work and we don't want to have to destroy anything they did.
Looking at the current state, on the video, you can see we got the turbojet engine self-sustaining on propane. The real key to getting that self-sustaining was getting a new pressure regulator so we could push more fuel into the combustion chamber. We also improved the oil properties by preheating our oil so it's running at the right viscosity, and we had less losses in the bearing system there. And then we also improved the ducting system. As you can see, there's some smoke, and that is all getting vented up into the ceiling. There's 2 vents above. And then we also have a better boom to prevent carbon monoxide from going off of the room.
So fuel injection is a very complex topic because liquid fuel will only burn when it's in the vapor form. This is actually true for anything burning. It's not actually burning the solid thing. It is turning into a vapor and then it's igniting. If you took a match and dropped it into a bucket of Jet A fuel, it would not ignite. So we have to do one of 2 methods to ignite the fuel. The first is atomization, where you break up the fuel into very, very, very tiny droplets, which then increases the surface area and makes it evaporate and burn much quicker. The second option is pre-vaporization, where you turn the fuel into a vapor form using a lot of energy in the form of heat, and then you ignite it the same way you would a gaseous fuel. There's a lot of trade-offs to these, but we decided on atomization using our decision matrix for many main reasons, which the biggest of these is the simplicity of hardware implementation and controls. If you want to use pre-vaporization, you need to create a lot of energy and you need to control it very well. If you vaporize too soon and you have air in your fuel line, you could ignite it within the fuel line, creating an explosion, which is really dangerous. And if you don't vaporize it before it enters the combustion chamber, then you just have a liquid stream of vapor entering your combustion chamber, which isn't going to burn. So atomization ensures that our controls do not have to be super, super expensive and that the fuel delivery will be all right. But atomization is very difficult because of manufacturing difficulty. There's super tiny fuel lines and air lines within this injector that you'll see in the future, and manufacturing that can get very difficult very quickly. From there, we have to choose our atomizer type. So there's a ton of different types of atomizers. Some of the main ones are here, but there's a lot more that you can research, which we did a lot of research on all the different types. These are the main ones that we focused on, with the left-hand side being pressure-based atomizers. The top left is a plain orifice atomizer where you take a high-pressure stream of liquid fuel, send it through a very small opening, which then bursts it into a bunch of different droplets. It's very crude, but it's very simple. Below that, you can see a simplex method, also known as pressure swirl, where you inject the fuel tangentially. It swirls to create a very thin cone, and then that cone is very unstable, and that breaks apart into tiny droplets. On the top right-hand side, you can see a simplex injector with air assist. So you send air on the outside of that cone, then swirl in the opposite direction or the same direction to further atomize that fuel. And below that, you can see another type called air blast, which uses a much higher flow rate of air, which isn't applicable to our system because we cannot produce those high flow rates of air. We decided to choose these 2 methods, again, because plain orifice is very simple and very crude. We'll be able to iterate upon that method and change based on testing. And a simplex air assist will be very predictable. So we can do a lot of mathematics and predict the performance of it. But once we build it, it will be very difficult to iterate. So we're going to design 2 designs in parallel and pursue them at the same time. That way we have one working one, and if we have 2, then we have another parameter to measure within our engine.
So looking at the liquid fuel selection, these are some of the liquid fuels we looked into. Jet A is a great fuel. It's the aviation industry standard, has fuel properties that would be good for our system, and it's easy to atomize. Kerosene is a less refined version of Jet A, so it has some more impurities in it. Sustainable aviation fuels is mostly Jet A, but then are made in a more environmentally friendly way. Those really are expensive, so kind of out of our price range. Gas is great atomization, but it's super dangerous to store, so it can easily ignite, and it's a real safety concern in the lab setting. And then diesel has poor atomization qualities, but it is easy and cheap to acquire. After looking at all that, we decided Jet A was our best, fuel to go.
So a critical first step before actually designing individual injectors was to find the fuel mass flow range. Why that's important, because the fuel mass flow or the fuel flow range is a critical variable in deciding the injector. And so the first step in that is actually finding the airflow range, which we use the compressor map for. This is the BorgWarner S206 compressor map from our turbocharger. This gives us an idea for some of the operating points our engine would be at, along with the assumption that we'd be using a propane-based startup, meaning we'd reach a self-sustaining propane-based system or cycle before induced or including liquid fuel. They give us the following range, 18 to 50 pounds mass per minute. Then we did a thermodynamic analysis of the combustion chamber. So we made some common assumptions for things like combustion efficiency, heating values with fuel, specific heats, along with some temperature data that we gathered from experiments and testing. And so using that, we found an equation for the fuel air ratio. With that fuel ratio and the air flow rates, we then determined the fuel flow rates and the fuel flow range. However, an important consideration of this is the delta P. Delta P is defined as the pressure necessary to push a certain flow rate through an injector. And why that's important is because delta P scales to the square of mass flow range. So that basically means for a wide flow range injector, it could become unfeasible due to high pressure requirements for the pump. And we firsthand saw that when we had an originally wider range, we couldn't find a pump that was capable of meeting those pressure requirements and within our budget.
So for our plain orifice atomizer, since we're limited to that $2,000 constraint and, a more expensive pump would produce a higher pressure, we're gonna not be able to produce, those higher pressures. So in our flow regime that we'll be working with, we decided to use an impingement surface as well as an air assist to make sure that we're maintaining stability as far as our atomization quality for our entire kind of low flow regime that we're working with. So an important performance metric that we evaluated for our fuel injector was the solder mean diameter. So in Lefebvre's book for atomization sprays, we found some SMD calculations, which is the average droplet diameter for an atomized spray weighted by surface area. So for our SMD, we have the velocity of the liquid, which is UL, and then the ambient pressure, which would actually be the pressure inside the combustion chamber. So that's going to change depending on what pressure ratio we're pushing. And then the velocity of the air, because we have an air assist component, and then the density of the air. So as we increase the orifice size of our discharge, we're going to have an increasing diameter of droplet. So we want to have a smaller discharge to have a higher quality atomization. So talking a little bit about our impingement surface, the design of that, it's important to understand what kind of breakup mechanisms are at play here. So we have two different kind of mechanisms that are happening. The first is you have pre-atomized stream due to a angle that's discharging from the plane orifice, and that will create kind of a film on the impingement surface. So from that film, we'll have a air assist that would come in and act as a shearing mechanism that would then break that up into tiny droplets. As well, we also have non-atomized stream that's exiting from the plane orifice, which would just automatically shear into small droplets upon hitting that impingement surface. So you can see we have a CAD model of our current surface on the right here, which is angled as to help kind of propagate the spread of that spray. So determining the geometry sizing of that plane orifice, we have this equation also from Lefebvre's book for atomization spray, which talks about the pressure gradient. So this would be the liquid pressure that's entering the atomizer, and then the ambient pressure condition. And as we have an increasing liquid pressure, we would have a narrower spray angle. So we want to design to that higher spray angle point to ensure that even at our lowest flow, we're having as much of the liquid stream at the impingement surface as possible. So this is the atomizer design that we came up with for plane orifice. We have an outer and inner air channel, and then that inner line, then the air would impact the fuel at right about where the impingement surface is at the top there. So one of the things that we have to think about is producing the best kind of air fuel mixture as possible inside the combustion chamber is how we're going to position the atomizer inside there. So we have kind of just a rough CAD here of how the injector would be positioned inside the combustion chamber. We have it about right before the main first air recirculation region to hopefully produce the best air fuel mixing. But one of the struggles with this design is there's no great way to predict what that cone geometry is going to look like after the impingement surface. There's not a lot of literature on that and a lot of study done. So we're planning on creating a test stand during the second semester so that we can measure what that spray cone angle is, because we really want to have the spray cone intersect the
outer angular, part of the combustion chamber, right about where that first air recirculation region is, to have the most optimal air fuel mixing. So we're also gonna, verify that with some CFD analysis as well.
I'll look at the other design we pursued in parallel, that being the pressure swirl. We had a few key considerations we did before, had before starting the design. So one, that fixed combustion temperature Noah just talked about. We have a relatively narrow inner liner wall so that we don't want to impinge on before it fully atomizes and evaporates and combusts. Second, the pump pressure limits. Those set a hard limit on both the pressure and flow rates through the injector. And third, the propane startup. When you have an already established combustion with propane, it's much easier to light liquid fuel. And so that means we can get away with a higher starting diameter, which will evaporate slower, but since it's already combustion, it's easier to light. And so with those kind of considerations in mind, along with some literature data and research on these types of injectors, we set some upper and lower design targets for things like the delta P, the spray angle, and the acceptable sodomy diameter for both a stable and effective atomization. And so looking into the analysis, we first defined the key parameters or key dimensions and variables. That being the inlet port diameter, the swirl chamber diameter, and the discharge orifice diameter, along with fluid properties and fluid flow rates. Then we found, in literature, we found experimentally verified correlations for things like sodomy diameter, the spray cone angle, and delta P, given those variables. And in parallel with that, we also considered several non-dimensional parameters. These had two purposes. One, these non-dimensional parameters verified that the correlations above were valid for the given dimensions we were testing. And two, these non-dimensional parameters also gave us a sense of, or gave us ideas for dimensional ratios that would allow for a stable spray, as well as minimizing losses across the injector. With those correlations and keeping those non-dimensional parameters in mind, we began an iterative procedure of setting the initial dimensions, then tracking how they vary. So for example, with this graph, you can see we're varying mass flow rate. The result of that varying mass flow rate on delta P, full cone angle, and sodomy diameter. Looking at different dimensions, how they vary the outputs. We then iterated the dimensions until we reached a desirable outcome. That being minimizing delta P for fuel pump stability, minimizing SMD for atomization quality, and also keeping half or full cone angle at in a desirable range. And so the result of those iterations gave us the final geometry you can see right here. You can also see how the swirl chamber and discharge incorporates one of our injector components that is part of a larger assembly. On the left here, you can see some of the baseline performance. This is at the minimum flow range. Most importantly, the spray cone angle, 44.3 degrees, is above our minimum that we set at 40 degrees. So that guarantees a stable spray. And second, it's also not too wide. You can see in this schematic here that it would first pass the primary liner holes where there's significant recirculation. The fuel would effectively mix, evaporate, and combust before impinging on the liner holes. And then second, the sodomy diameter is 57.8 micrometers. That's below our 70 micrometer maximum and well within our range. So we can expect relatively good atomization and combustion. On top of that, we also actually wanted to add a swirl air assist system to further improve flow and atomization. How we want to achieve this would basically create a cone of rotating air that's external and concentric with the fuel cone. What this does is effectively increases the relative velocity between the fuel sheet and the air, inducing shear stresses in the fuel and accelerating breakup mechanisms. And so we can see how we achieve that is we have vanes on this outer blue piece. It adds a tangential component of velocity to the air, causing a swirl and a cone. And then in terms of feasibility, we assume some modest air flow rates and modest air velocities. We found that it could reduce the sodomy diameter by over 40%, which is a very significant reduction in sodomy diameter, improves atomization and then combustion quality. And then second, we also did a quick feasibility study using CFD. This told us that we only need around 20 kilopascals of pressure in order to push those modest airflows through the nozzle here. And so that's well within the range of our shop air supply that's available right now. So now looking at the final configuration design, you can see the full assembly and also how it's installed inside the combustion chamber as well as the labeled parts. The goal of this assembly was to make it both modular and manufacturable. So there's significant problems with each individual component. How do we simplify it? How do we reduce the number of parts? And how do we make it manufacturable with the tools we have here at MSOE? In terms of modularity, you can see that things like the adapter, fuel line, and mounting surface are actually cross-compatible between the two designs that Noah was had in mind. And then we also considered several different types of joints or fittings for the different parts to join it together. So things like interference fits, brazing, threaded, and welded joints for a variety of different sizes and also purposes. And in terms of material selection, we had 4 key criteria, that being corrosion resistance, fuel compatibility, high strength at elevated temperatures since we're inside a combustion chamber, and third, relative ease of machining. All those criteria point us towards stainless steel, more specifically 304 stainless steel, which will probably make up the majority of our components. We also ran a simple FEA for this to verify that none of our parts, specifically the fuel components, would explode.
Looking at the overall fuel delivery system, we have a schematic of all the components we plan to have. Some of the major ones are obviously the fuel tank, that's gonna hold our jet A fuel. Then we have a couple of pumps in series, so that way we can add the pressures and achieve the pressures needed for both of our pressure fuel injectors. We also then have a series of valves, pressure relief valves, as well as gauges, so that way we can have key instrumentation on the line. We also had a mass flow or fuel flow sensor in there, so that way we can have this for lab use and be able to have key parameters. And then we have finally the injector, which we just discussed. Those injectors will be able to be interchanged so we can test both on our fuel delivery system. And then looking at our budget, we have about $2,000. We've already spent $200 approximately on the upgrades to get the turbojet self-sustaining. And then looking forward to second semester, we had plans to spend another $100 on the permanent heating solution for our oil. And then we have $1,100 budgeted for the fuel delivery system. Big cost there is going to be the pumps. And then the fuel injector, we have budgeted $600. We plan to manufacture in-house, but we have prototypes as well as a test stand and just iterating on it. It will add up to about $600 we have budgeted at least.
And for our second semester timeline, we're planning on prototyping these fleshed out designs during January and February, which will be then constructing a test stand to better determine what that cone geometry looks like after the impingement surface, so we can determine what's the best positioning for our fuel injectors within the combustion chamber. And then for the end of the term, we'll be creating some documentation as how this could be used in a future lab setting.
These are some of the people that we've worked with over the course of the semester. We're really grateful for everyone's help, especially Dr. V for being our advisor. And we're really looking forward to collaborating in the future. And with that, we'd love to answer any questions you have.
Could you talk a little bit about the self-sustaining aspect, that how it wasn't self-sustaining before, and what you're looking for now, and then the incorporation of propane?
Yeah, definitely. So I'll go back to our current state slide. So coming into this year, we had a turbojet engine in the design last year. The main things that we changed that did allow us to reach self-sustaining points was adding a bigger pressure regulator. So we can now push up to 60 PSI of pressure. Last year, they were using 20. And in addition to that, we use a leaf blower for startups. We attach a leaf blower to the compressor. The leaf blower that they had last year was an axial leaf blower, meaning you could not push against the blockage that the compressor creates. So we got a centrifugal blower, which can push past that. Those two things allowed us to create higher pressure ratios. We got up to 1.6, which last year they couldn't get above 1.2, and also run it at that high stable compression ratio with relatively stable temperatures. So the video is not playing right now, but we can now get to self-sustain and hold a stable temperature between 950 and 10,050 or 1,050 degrees. And in the video, you can see that pushing it was generating. So that was something that they couldn't do last year that we did change by adding that pressure regulator in the blower.
So what would happen before you made this?
So we have that blower that's blowing the compressor. It was basically powering the entire system. So if you took off the blower, it would just slowly stop working.
It runs on fuel alone now, once we get it up to the RPMs that are required to have that pressure issue.
Yeah, so we know it's self-sustaining if we take away the blower and it keeps going.
Question. How many injectors do you have?
The injectors? Yeah. Well, there's currently one propane injector inside, and we're gonna have two different fuel injectors that will have into them incorporate a propane injector as well. So in total, technically 3 once we're done that you can interchange, but we'll likely just be switching between the two fuel injectors or the liquid fuel injectors that will have propane incorporated as well. So if you're interested in how that works, I don't know if you want to go through that last slide or the air system. So yes, yeah, this one. So with the liquid fuel injectors, this is the fuel injector part for the liquid. So for the propane, we'd be passing it through the air shell component. So we'd be replacing the propane injector that we currently have.
Do you have any cooling system anywhere, like in the anywhere, like in the system?
So
for the fuel injector itself, or
no,
for the
like for the combustion, like chamber.
We only have, so I don't know, do we have the oil system? Either way, we only have a cooling system for the oil, because the main purpose of the oil is to both lubricate and cool the turbine bearings. And so.
The only heat exchanger or system for that was for the oil, and when we were doing our analysis, actually, I'll go back to the current state slide again. We discovered that last year they were running on oil viscosities that were much too high for the turbocharger. So they were using a heat exchanger in that system, but we eliminated the use of that heat exchanger because we want the temperature of the oil to be much higher. The rest of it doesn't have any cooling system.
Right, so you can see this is the oil passing from the turbine bearing housing. But you can't see the heat chamber, but it's back here. It's actually not functioning because we don't want the oil to be cold. We want it to be elevated temperature, have better viscosity. And it stays around 50 degrees Celsius, and we can probably push it all the way to 100 degrees Celsius safely. So the cooling system is not necessary in this case.
Okay. You mentioned measuring the spray angle. How
Yeah.
were you planning on doing that?
We were planning on doing kind of like a particle image velocimetry analysis, so like having a kind of a grid backdrop and then measuring through like high frame camera, like seeing where the spray actually goes and then measuring that angle, so.
Follow up to that, did you have any plans to try and get droplet size measurements experimentally?
That's probably on our scope.
Yeah.
It's very difficult. We actually went on a tour of the Collins Aerospace facility, where they do a lot of fuel injection design and testing, and they have machines that can do that, and it's insane how complicated that technology can get.
You mentioned that Jet A was difficult to get, but that's what you're going to use.
Yeah.
So I'm wondering how you're gonna get it. And then the other thing is as far as the injector design and heating values and things like that, how much difference is there between the different fuels you were looking at?
Yeah, so to answer that question, the heating values, all the fuels on this page here, they're all relatively similar to that of propane, so we don't have to redesign the combustion chamber. And then obviously, acquiring Jet A is a little bit harder than just going to a gas station and pumping some into a can. But we talked to Collins Aerospace and they recommended going to the airport. And you can usually ask for some Jet A that way. And then additionally, we were discussing that deplane Jet A fuel is usually relatively cheap compared to just like Jet A that was hasn't been in a plane yet. So we're planning on trying to get some deplane Jet A and just going to like a local airport. Yeah.
Is there much difference between, when you say kerosene lacks consistency, is that based on the source and aviation fuel?
Yeah, so aviation fuel, it's Jet A specifically has much higher standards. So when you get Jet A, you know what you're getting. It's going to be very consistent throughout, which is good for repeatable testing. And then kerosene, there's obviously going to be a little bit of variation. It's just not as highly regulated. And so then that could lead to like potentially coking risks with different things.
Yeah, kerosene, the regulations for tiki torches probably for it. So,
yeah.
You mentioned you didn't have to do a combustor redesign. Are you going to get complete combustion? And do you plan to take a look at byproduct analysis at any point?
No, well, no, just the range for. Well, so I guess what Connor mentioned that we want the similar heat values to propane so that we have similar fuel air ratios in that interliner. And since their design has been proven to be stable, to have stable combustion at that fuel air ratio, that's where we're basing off stable combustion. At least it's having similar heat value and similar fuel air ratio, therefore it's a propane. In terms of exhaust products though, it might be possible, but it's I guess more complicated. So we need a temperature inside the actual flame to get estimates for that. But I guess if we can figure out a flow split, then we can back calculate from the exhaust temperature and figure out what temperature you're getting inside the inner liner. And then maybe figure out some sort of exhaust properties.
We have time for maybe one or two more questions.
Noah, how big is the impingement surface? You had some unit or some numbers on there, but there were no units.
Yeah, so kind of give you, this is in all millimeters, so like the plane orifice is actually 0.635 millimeters, like it's really small. So that's one of the difficulties of machining this, is that's 4 millimeters in height. And then if you're actually looking at cross-sectional area of some of those bridge sections, it's about 1.5 millimeters. It's pretty small.
You guys had mentioned hand machining. Is that on the table for this component, or are you gonna have this done with CNC?
Potentially on the table. One of the other things that we've looked into is having this additively manufactured at Collins Aerospace. So that's also a potential option.
Any last questions?
You know what a process they would use to build something like this? It's a laser sintering, I want to say. It's 3D printed lasers for a bed of ink canal. That's what they use generally for their components.
They've got two $500,000 machines that are the size of a small house. It's insane.
And you should have like 12 lasers that work all at the same time. It's pretty cool.
Why then that's why you get more of those. I tell you.
Because we're not college aerospace.
I guess one last question. Did you do any calculations to make sure you weren't gonna get any backflow in terms of?
On the liquid fuel side or?
Yeah,
I mean, the relative pressure of the, well, I guess for the pressure swirl, there's actually an air core, so inherently there's gonna be air going into that swirl chamber. But other than that, the pressure of the fuel is on the order of hundreds of pascals. It's more likely than not around 12 atmospheres on the high end. While the combustion chamber only goes to at most 3 atmospheres. So we're assuming that there isn't gonna be any backflow, and there is also check valves incorporated if you want in case there's gonna be backflow.
all right. So with that, we'll go ahead and thank this group. And next up, I believe we have the Delta Hawk composite engine block. So who gets to design the control system for all of these pumps? No? All right. So, ooh, slightly longer than the F1, you know. I know it is. It really is. So. All right, looks like we have everyone here. So at this point, we have our final presentation of this first session, and I'll turn the floor over to you guys.
Yeah, then I'll punch you. Victor? Let's go first, so yeah.
Yeah. So basically, it's just everything we're going over, just our design considerations, terminology, so you guys understand the words that we're using. Some of them aren't like super self-explanatory. Our background, when we looked at for our engine, anything similar to what we did to make sure we weren't stepping on any toes. And then materials manufacturing, our down selection, and our model with some analysis. So first, a little bit about Delta Hawk. They actually sponsored our project for us, so they're basically we're talking to them about it. They make basically their own aircraft engines. They're testing. Some of them are more like experimental, and they're down in Racine, but they look to improve engine efficiency and more affordable. So they do a lot of like diesel type engines, which use usually more jet fuels. And then basically they're trying to increase flight range and make it so that it's easily accessible for customers to buy and stuff.
So moving on to our problem statement, Delta Hawk is developing a 2-cylinder horizontally opposed engine that is currently too heavy for the desired drone applications. So they're requesting us to design or redesign the engine block to be lighter than the current aluminum model that they have. And kind of expanding on this further, the weight to power ratio is very critical for drones and aircraft in general, because as you reduce the weight, you increase the fuel efficiency. You can also increase the amount of payload that you can carry. And then with the engine block is typically like the heaviest part of the engine. So that's why it was identified as like a critical part for reducing the overall weight.
Objectives, constraints that we had, so some of our objectives is that it needed to fit within a 16 by 24 by 14 inch space. That's what was allotted for us. Can't go anything bigger than that, but we can be smaller. It should weigh less than 100 pounds when fully combined. So that includes the engine block that we designed and the components that they give us. And then the composite itself needs to withstand like standard temperature of around 240 plus exhaust temperature, which they didn't give us. So that's something we had to find. And some of the constraints that we had is it had to be compatible with the Delta Hawk parts they provided. So cylinder head, coolant ports, all like the piston assembly, stuff like that. It gave us a liner as well that it needed to be compatible with. It had to withstand thermal gradients due to combustion and just being an engine. And then the composite cannot react with the fuel and the coolant that it is in contact with. And then it's about 10 to 20 flight hours. So here's kind of a basic form of the engine that they gave us with the terminology we're using. So the coolant ports, where the coolant goes. The cylinder liner is an aluminum liner that they give us for the piston to travel inside of. And then the connecting rods connect all the pieces of the engine together. Like you're housing, the crankcase is the main thing that we were designing along with the cylinder housing, which is going to be mainly where the piston is. Our rod channels are kind of these extruded pieces on the outside, and then the cylinder head is what they gave us.
So we did some subsystem assignments just to delegate a lot of work that was being done. Danny focused a lot on thermal combustion analysis along with the mounting and fastening of the different components of the engine that we'll talk about. Victor looked at the manufacturing materials that are involved along with the FBA for the casing. And then I focused mainly on engine components, was the modeling lead, and did FBA for our cylinder. So a little bit about boxer engines, we said before, is they're horizontally opposed pistons and combustion chambers. So some of the benefits of that is that there's very little vibration, and we can essentially eliminate that from our evaluation. We won't need to consider that. Has a flat profile that can be mounted low in the aircraft as well, which is great for stability. And that low profile also helps to reduce drag, which again is extremely important for drone applications. Some of the drawbacks though is more complex engine in terms of like the valve train and coolant that's going on. So that'll obviously increase the manufacturing as well, along with increasing more modes of failure. And there is some increased maintenance, but due to our flight time of 10 to 20 hours, that's not a concern, and they're making one-way trips. So this is a kind of a piecemeal model that Delta Hawk gave to us, just pointing out some of the components. We've got the piston location inside the cylinder liner, and then these holes are the exhaust ports. We've got the connecting rod here below the exhaust ports and some of the train head components. So we've got the cylinder head, which is mounted to the rest of the engine using these threaded connecting rods. The cylinder liner, a coolant nozzle, the water jacket will be in this region, crankshaft, and crankcase.
Some background on combustion, just so that we understood kind of what was going on inside the engine, is that it's a compression ignition. So again, that diesel, so no spark is actually used to ignite it. It's all compression based. And then it's generally more efficient to be a diesel engine, which is good for us just because it is so small with such a short time. And then some factors that are influencing combustion are things like inlet temperature, your combustion pressure, the actual fuel that you're using, and some other factors that we didn't have to look into just because it was designed for us. We just had to edit some of the designs that they made to make it composite based. So then this combustion analysis can also help us determine like exit temperature and adiabatic flame temperature. So basically to make sure that the temperature that we're output is stand. So just looking into how to calculate things like that. And then, so different fuel distillation methods are going to affect how the fuel burns. So just understanding that with our fuel that's being used, which was Jet A fuel, not diesel. So a lot of this we didn't necessarily have to consider because it was designed for us. They didn't, but we could like edit some of the things around it.
So moving on to some background research on potential manufacturing processes. The one on the left is called reaction injection molding. So you have that raw material in liquid form that's injected into a closed mold using the sprue, and then it adheres inside the mold. Some benefits of this process, you get really fast cycle times, and you can also produce some really complex geometries, which you saw from the initial concepts that there's a lot of that associated with the casing. And then on the right, we have compression molding. So this one uses an open mold where you place the raw material in that bottom mold there, and then you have like a hydraulic press that presses it and then flows and fills the entire mold. Some limitations of this though, is the ability to form like thin walls and detailed parts because the resin is a little bit thicker in viscosity, so it doesn't flow as well. But you can achieve higher volume fractions with that hydraulic press, which is like the reinforcement material, which leads to stronger parts. And then some background research on potential materials that we could use. You can see here compared some of the tensile strength values. Not much variation here because they typically use the same reinforcement material, which is like glass fiber. So the variation there is based about like how much of that reinforcement you have. But you will see a lot more variation in the thermal properties, varying from about like 300 degrees Fahrenheit all the way up to 680 degrees Fahrenheit. But as you increase in those thermal performance, you're obviously gonna have that increase in cost. So it was kind of critical to balance those two criteria.
So we did a lot of background research like we've been talking about, and we looked at material testing, laboratory experiments, came up with a few patents that were from the 80s and 90s from Ford Motor Company. Ultimately, we focused a lot on a SAE article that was written by Dr. Tony Coppola, who works for GM and did a composite cylinder. He didn't do the crankcase or involved any exhaust region, but the cylinder of the engine, including the water jacket. So we drove a lot of our concepts and ideas off of this design. And you'll see that with our final model. We were able to get in touch with them and get some information on what the important aspects of this project were, where high stresses were, high temperatures, and some factors we considered that we saw in actual testing.
So moving on, we did our down selection for manufacturing processes. Some of the criteria that we kind of prioritized here was the production cost, the geometry complexity, and the material properties. So with production costs, they wanted this to be like a low cost solution because these drones aren't going to be used for very long. They have a very short life cycle. So you don't want to spend a lot of money on an engine that's not going to be used a lot. And then for like geometry complexity, you need to form this to be complex in shape. And you can see we included some other processes that we didn't talk about. And we kind of ruled those out right away just because they aren't capable of producing those complex geometries. And part of the complex geometries is being able to form the composite as much as possible to the shape that we need. Because you don't want to do any post-process machining if possible. You want to limit the amount you do. The reason is because composite materials are very brittle. So when you machine it, you can get micro cracks in the structure, which will reduce the mechanical properties of it. And then comparing like material properties was important because obviously in the engine, you're going to have a lot of thermal mechanical stresses. So it's important that it can produce strong enough parts to withstand that. And then ultimately, we ended up choosing reaction injection molding as our process because you can get the most complex geometries with it. And you've got really fast cycle times, which decreases the production cost. And then we also have that extra benefit of having a connection to a potential manufacturer called Sumitomo Bakelite. So they're actually the ones that manufacture that composite block for GM. And Dr. Coppola gave us a contact to them, which is very beneficial. So he kind of explained them as like a one-stop shop for this. So they design and create the mold, they supply the raw material, they actually manufacture the part, and they do in post-processing. So it kind of reduces complexity of having to find multiple manufacturers or vendors. And then moving on to our down selection of materials, prioritizing cost again, and also prioritizing the thermal properties because we kind of identified this as like a critical area that the material might fail over like mechanical properties. So we ended up choosing phenolic molding compound because you can achieve those very high thermal properties, similar to the higher performance materials, but it is also a very low cost material. So Dr. Coppola gave us an estimate about $5 to $7 per kilogram, which is not very expensive. So you got the best of both the cost and the thermal properties there. And then you also have that extra validation because this is actually the material they used in the GM composite block. So we already had a similar test case that it's being used. And then we ended up choosing like a specific material to go further with like our FEA analysis. So this is from a company called Plenco. They're a local manufacturer of composites. It's got a tensile strength of about 16.2 KSI, heat deflection temperature about 420 degrees Fahrenheit.
Also went through the process of creating a bunch of different ideas for the actual engine block itself, because the one that they initially gave us was very basic, and then when they edited it, it was too complex for manufacturing processes. So we went through kind of look to see how we could break it down to be manufactured properly. So we thought about breaking it down into quarters, so this is kind of like 1/4 of it, but then we were cutting our cylinder in half. We didn't want to do that for leakage purposes, so we kind of ruled that idea out. And we also thought about maybe attaching an extruded piece onto the side of the crankcase so that the cylinder itself could be all one consecutive piece. That changed the geometry of the crankcase a little bit, and we wanted to try to keep the crankcase as close to what they gave us as possible. Because we know they put a lot of time and effort and money into creating something that they already knew worked. So we decided that we should probably try to keep it closer and not have this extruded piece on the side. We also looked into like mounting of this piece or just the crankcase into here, and decided to maybe look into having an extruded piece outside versus the internal holes and having bolts kind of connecting it in. But we were a little bit worried about the stress here and also changing the actual geometry of the part and having it be bigger, and so then it wouldn't fit the parts that they provided as well. So this is kind of the closest to our final design, where you have a separate crankcase that's a little bit from the like cylinder housing. And then this is a little bit squared off with some rounded geometry to it so that it could fit well. And then it's cut in half so that you can manufacture 1/2 the cylinder, the other half. And there's another mounting kind of picture that we looked into, just because they didn't give us how they were going to mount it because they didn't know, but we wanted to make sure whatever we designed could be mounted if needed.
So this is our current model. We're very close to a final design. Currently it's 24 by 11.4 by 9, and our mass estimate with the material that we've chosen is 9.8 pounds. So this is also a cross section view looking at the components. We've got a heat gasket and fire plate that are installed. We've got a coolant flow that goes into the water jacket region, and that's separated using it from the exhaust region using O-rings. Currently there's 2 O-rings, another one will need to be added. But this is the model we have so far.
Then we are using threaded inserts to put the connecting rod into the composite, because as stated before, you want to do as little like post processing as you can, and you can't actually like drill the threads into the composite. So we did some math based on the combustion pressure forces that were then applied to the bolts and divided that by 4. Came out to, I think it was 28,000 PSI. That was what it was. So we found 2 that were above that so that it would resist pulling out from our composite material. And so this one is these 2 are from Sherlock, and they are a little bit more focused because this company only does like threaded inserts and threaded rods. So these are going to resist pullout, and they have an extra attached lock ring, so that gives that little extra force. But the ones that we actually used in our model were from McMaster-Carr because they are a little bit cheaper. They're easier to get in small quantities just for testing and experimental purposes. And they still provided the same pull-up that we needed to resist that so that they stayed in the part while also being able to be like edited if we needed to. And then I also did some combustion calculation setup. Because we didn't have all of the information to actually do a full combustion work through until later in the semester when we had already focused on other things. So this will be a over winter break to next semester. So basically just setting up kind of how the combustion works, making sure that everything is balanced out so we know how all of the different products react with the air and the fuel. And then working on adiabatic flame temp, which is basically just the maximum possible temperature that could be produced by the engine, just saying that anything that is produced, like all the energy is used to reheat versus leaving the actual engine itself. So here's the setup for that.
I did the cylinder on the FEA. So on the left, I created a simplified version of the model that you saw before, just to reduce the number of elements and nodes and the loading time of the model. So I applied the combustion temperature to the inside of the cylinder, along with a steady state thermal condition of the max temperature that our coolant would achieve. And then I had to assign boundary conditions to the bolt holes to make sure that the system was steady stable and produce accurate bolts. So the bolts going through those 4 holes, I put free in the X and Y component due to thermal expansion contraction. They can move, and the C component fixed it, since they shouldn't come in and out of the bolt holes. Rotation X and Y was fixed since the rods aren't going to twist against the cylinder, but it can't screw out of the cylinder, so that's why the rotation is free. To confirm that the boundary conditions were correct and ultimately FDA results, I took the simplified model and just ran some basic calculations. So I looked at the reactionary forces on those bolt holes compared to the mechanical calculations and got 0% error. I did this in another case looking at the cylinder liner. So evaluating the hoop stress that was achieved and then comparing that to hand calculations and got less than 2% error. So I can know that my boundary conditions are correct. Some of the main components that we're concerned about are shown here. It's not a complete FEA result. We still have to include the actual combustion temperature and the exhaust temperature. Region 1 is the highest stress portion, the water jacket, which we're not concerned about due to the GTP or the glass transition temperature of our phenolic being anywhere from 200 to 250. And then region 2, that's an easy change by adding a larger fillet and more natural geometry. This will also help with manufacturing as well on resin flow. Area 3 is a high point of concern and something that we'll be taking into consideration fixing in second semester. So to the research that we've done, nobody's put exhaust temperatures in direct contact with composites before. So we're going to have to add some sort of aluminum liner just due to Delta Hawk saying that we could experience up to 1,000 degrees F in that region. Some minor changes that I'll have to make is adding another O-ring at the top to separate the water jacket region from the top of the cylinder head, and then shrinking that region as much as I possibly can that manufacturing will allow, just due to the high temperatures that are experienced at the top of the cylinder. And draft angles will have to be added. That's something that we will talk with manufacturing about. For FEA, a few steps, like I said before, adding combustion and exhaust temperatures along with modifying the engine temperature.
So we also performed an FEA analysis on the entire half of the casing. This was kind of to analyze the results of the bolt preload between the two halves. So you can see those right here. We were able to estimate the amount of preload using this equation, which is the torque over the nominal diameter times the nut factor. So Delta Hawk actually gave us their torque specs for each bolt, and we were able to estimate that. So 7/16 bolts are the 4 on the two ends. So here, there's 2 more on this end. The 3/8 are these 2 right here, which are fastening down on these posts here. And then the 5/16 along the edge here. And then we also applied that pressure inside the combustion chamber. And this is the result of that. So we end up getting a max stress of 92 KSI versus our strength of 16.2 KSI, which is giving us a factor of safety of a lot less than 1. So it's occurring right here in this in-between region between the support post and the main body. So that means we have to do some design changes next semester. Some things we can do is increase this cross-sectional area here so the force is distributed over a larger area. We can increase the fill radius here because you can see that would reduce the stress concentration there. And then another thing we can do is change the torque specs, reducing them, because the torque specs that Delta gave us were designed to run an aluminum engine block. So we would need to make our own for a composite engine block.
And they were estimating hundreds of cycles, thousands of flight time hours.
And so next step, just for the thermal combustion analysis, basically with the given text they gave us, the airflow rate and the temperatures and combustion pressure, which again, all things that they gave us, we can go through and calculate the exhaust temperature and the adiabatic flame temp to then apply to those to make sure that the combustion process doesn't break or fracture our composite.
So just kind of some closing notes on what we're going to be doing next semester is, of course, we have to get our NDA signed and then we'll contact Sumitomo Bakelite for some manufacturing consultation, hopefully get a quote maybe on materials and also manufacturing. Currently our material cost estimate, we estimate our composite engine block to be anywhere from $20 to $40 per unit. That does not include upfront capital, which could be anywhere from $10,000 to $500,000. So we'll be reaching out to a company called Plenco as well. Or haven't heard back from them yet, but we also have another connection that we just heard about on Wednesday that we'll be trying to contact. Have to change how the exhaust interfaces with our composite material, have to do some torque spec modification, possibly do our own torque study. And then consider mounting us down the final base. And this is somewhat of our tentative schedule. Get NDAs hopefully by the end of next week. Make changes to our model. Second week coming back, get some rough quotes and share models, and then eventually get a 3D printed model that has combinations of actual components from Delta Hawk to have one full engine. Thanks. Questions?
You said something about one-way trips. So these things don't come back?
No.
Nope.
We don't know what they're for, it's just one,
We haven't mentioned.
yeah. It is directional flight.
So, I mean. Okay, then, a lot of things that don't really matter from the standpoint of like.
And it's experimental aircraft, so we don't have to follow any FAA regulations.
Very useful. That's very useful.
Correct.
Very helpful.
Okay.
Yeah, so we don't have to worry about things like super short flight time, which helps us with the combustion temperatures with them.
But you said 10 to 20 hours?
Correct.
That's the flight time?
That's the estimated right now. They gave us one that was originally a little longer, but that's their newer estimated.
Interesting. Okay. Yeah, I can see why you have to sign an NDA. No, I did have, no, that, I was just curious, I was like, wait, is that true? Okay.
Question.
So a couple of things, so Victor, when you're talking about the composite manufacturing, where you're comparing the mold, the press.
Injection.
The injection, actually the other one. You mentioned something about how the disadvantage for, the second one, I think, was about the wall thickness and how you can't make it too thin. Did I hear you right about that?
Yes.
I was just curious about that, because is that not just a function of how much charge you put into it? So couldn't you make it as thin as you want by just putting less charge into the mold and then pressing it? Or am I misunderstanding the process?
I mean, you need a certain amount to fill the entire mold, so.
Agreed. But if you just put just enough, wouldn't that mean it would get spread out and it would be thinner? Versus if you put a ton, it would still spread out.
You have like areas that are for flashing so that they spread out beyond the mold itself, so it's not just a closed contained mold, it also expands outward, so it'd probably go into those flashing.
Okay.
Beyond the mold.
Okay.
We met with a local manufacturer, I can't remember the name, but they do compression molding.
Cornerstone Composites.
Cornerstone Composites. And there's a thickness at which they can achieve, but it's achieved by just producing flash.
Got it. Okay, cool. Coolant is water?
That's a.
And then, yeah,
Okay. So when you say water jacket,
jacket.
it's a coolant
It's a
jacket.
coolant jacket.
Okay, all right, that's what I was curious about, because I didn't know what the coolant was. And so when you talk about your material selection, you ultimately zeroed in on phenolic Quenco, right? And you said awesome thermal properties, awesome cost. Like, what's the trade-off? Because anytime I always hear, oh, this is dope on this front and this front, I'm like, there's gotta be a cost somewhere. You're taking a hit somewhere.
I mean, you're not getting the most extreme thermal properties, you're still get even higher.
Okay.
But then you're going like $200 to $100 per kilogram,
Sure.
it's just way more expensive.
Okay, so regarding that, my question was, how are you quantifying like sort of the heat resistance? Like that,
So the typical metric I found was just heat deflection temperature, which is like, they put it under a certain load, like 264 PSI, and they measure when it starts to deform under temperature.
and that is compression or tension or?
I'm not sure exactly.
Okay,
We're also focus mainly on the glass transition temperature of the material. Sure. And so we'll compare that to the values that Danny's calculated and we're providing.
Okay, sorry, I just had a couple questions. Regarding your adiabatic flame temp calculation, are you gonna model that as a constant pressure process? Because it's sort of a diesel-like.
Yeah, it would be at that pressure that he gave us, which I think was 140 bar.
Okay.
So it's gonna be. Today.
Okay, all right, that makes sense. And then, so from that, in your FTA calculations then, what temperature were you using if you don't have the combustion temperature? So maybe you said that, I missed it, so I apologize if that was the case.
Yeah, so I only have one temperature applied. The area in red is where I applied the maximum cooling temperature to everything in contact with that coolant. And then and I'll apply the temperature at combustion inside the liner and the exhaust temperatures as well.
So do you then anticipate the factors of safety to be even worse than what you have here?
Yeah.
Like if your factor of safety is 0.18, if you now include, is there a reason to think that it would be even lower than that if you have to worry? Or is that like so far away from the sort of the combustion region that you're like, it's not a big deal?
Yeah, we expect number 3 to go up substantially. So that's why we're going to have to incorporate some sort of liner in the sauce region.
The crankcase itself, it's far enough away from the combustion that one shouldn't be too affected by the increase in temperature. So just changing the geometry should help not get that.
Yeah, 0.2 safety factor right now is in the crankcase bolt area. Here, I don't know what your stresses are currently, but
yeah, this was just to show where the high stresses were, since I don't have all the thermal properties yet, just to see, okay, what am I worried about right now?
To focus next semester.
So it's functionally a pretty picture.
Yes.
it's a useful picture. When's it gonna be hot? Come on.
It will be used when we have temperatures.
Yeah.
But I got it all set up, so essentially I just have to plug in the temp and then.
But it's gonna be a fluctuating temperature. It's not gonna be a steady state temperature because, the temperature changes throughout the cycle. So if that's what you're gonna look to account for, because applying a steady state fixed combustion temperature does not include the cyclic loading, thermal loading.
Yeah, I'm kind of teaching myself here on thermal stuff. I mean, we're an FEA, and so we don't have anybody in CFD, but my thought process, and maybe it's wrong, that if I apply steady state conditions for the worst case temperatures, I can find the worst case stresses. Maybe that's wrong.
I'm not sure either. I would just have some hesitation about them just because the cyclic effects can create issues, but yeah, just something to think about.
We have time for maybe one or maybe two quick questions.
How much flexibility, if any, do you have with jackets?
So currently they have cooling jacket and model that they sent us, it's highly complex. So the location of the input and output are fixed. It's pretty limited.
It's very manufacturing based.
So.
Yeah.
Rocker already hit on this, the coolant, probably the flow rate, all of those are probably fixed. I mean, is there the potential for adding fins or veins or anything like that?
Manufacturing process small. Okay, for that. Yeah.
So, I'd say it's not impossible, because one of the ways that they're planning on creating this internal water jacket is like a bit of a lost wax sort of method. It's not actually a lost wax, it's like a lost metal, almost think like a solder that gets put into the reaction injection molding process, and then afterwards you can melt that out to give yourself that internal water jacket. That's generally kind of how it probably will have to proceed. We need to have conversations with the person that's going to manufacture the Sumitomo Bakelite company to get their recommendations.
They put in some the zinc alloy here, and after manufacturing, they were able to melt it out for additional fluid regions, and that's a way that we could get a more complex fluid region. But again, that's something that is more, we're gonna have to contact manufacturers since it's. I no idea.
Yeah, I just wondered if there's a way to reduce the temperature that you're gonna have to survive. If there's any way to modify the systems.
Sadly, the cooling region doesn't really go into exhaust at all. They have it in their model, but that's what they're design. Because they're producing channels that are extremely small with the design. So, that's something that we also kind of can explore.
One question. The figure that you showed from the being resolved, do you think that you have enough elements to fit this of the cylinder?
Here?
Yeah.
I suppose like, I mean, you're like two to three elements around the thickness, and I guess.
Yeah, I think you need more to the technique. So if it is too thin and if you feel it comes wrong, then maybe use shell elements for it.
Yeah.
And it structures like that.
Do you have a direct comparison between the original cost and weight of the parts and now the new ones you're proposing?
We know that their current model is over 100 pounds.
Yeah, there's over 100,000 like.
So don't yet have those comparisons. We don't have all the materials that they're using, or also they sent the models that they sent us are, I think they sent us step files, so everything's in one part, you can't break it down, but it's all one material as well. So it's kind of.
Like over 100 parts, like that's.
Yeah.
So that's the whole assembly versus your just.
There's aluminum materials,
Okay.
100, and our composite materials, 10.
For the casing.
Right.
Do you guys know how they're making their aluminum parts right now?
Or just a cast.
Just cast?
Yeah.
Yeah.
They're actually like developing this in tandem. They don't actually have it yet. They're kind of developing their aluminum model at the same time as us.
I'm surprised they're not pursuing AM, maybe, but.
We had a meeting with them on Wednesday and they were like, oh, look, we're glad to see that your direction is going where our direction is. So we're kind of doing it together. Comparing back and forth.
Yeah, answer the last question, the density ratio is 1.15.
All right, so technically, I think we're a little over time, so we'll go ahead and wrap up this question. We'll thank this going through. And I think we should go ahead and make sure to thank all of the groups here. You guys made it through your presentation.
Okay. Thank you for running the session.
Yeah,
Appreciate that.
no